So here we've got a little applet, and basically all it is it will give us a wave. It'll generate it over here on the left, and it'll move towards the right. And we're essentially looking at a little string. Each of these little dots could be one particle or piece of the string. And why don't we start with the fixed end? So this string is tied down right here. What this is going to show us is it's going to show us an incoming wave, which is going to look just like this. And then we are going to have a reflected wave, and the reflected wave is going to be shown in blue. The reason this is tricky, though, is because we're not just looking at a single pulse. We have a continuous wave, or a series of pulses coming in this way, and there's going to be a series of pulses that are reflected. So remember, because we have a fixed end, the direction of the pulse should flip over when it's coming out this way, and they're going to show that in blue. So let's take a look. All right, there we go. So now remember, we have two waves. We have the incoming one, and the blue is just the reflection of the incoming one, but the two waves are following the laws of superposition, and we can see that when they stack right on top of each other like that, they're adding up. And if we look at the medium itself, right, this is what's actually vibrating. The blue and the red are just sort of to help us see it. Those are the two separate waves, but what's actually vibrating is this black line here. These are adding together to give us really big amplitudes. But if we watch what happens as we step forward in time, look what happens when the two waves are opposite each other. They're almost canceling out, and the medium is almost totally flat. So what we have is this combination of incoming waves and reflected waves giving us this interesting phenomenon called a standing wave. And the cool thing about standing waves is that we've got these points. They're labeled with ends here. They're called nodes. And if you look at all those points, they're not moving at all. See those ends, those nodes, those points? They're not moving at all. And the reason for that is if we look at any given instant in time and we look at a node, the incoming wave, if we look at the amplitude of the incoming wave right at this node, it's like right there. And then if we look at the amplitude of the reflected wave, they should be exactly equal and opposite sign, but same magnitude, so that they're going to cancel out and give us 0. And that should be true no matter when we look at it. Like right here, we've got a peak on the incoming and then a peak on the reflected ones, but they're opposite signs, so the node is 0. And no matter when we look at it, the incoming and the reflected wave, the amplitude, or the amplitude of them at any moment will always cancel out. So those nodes stay at 0 the whole time. These other points where there's A's, those are called antinodes. And those occur right in between the nodes, and those are the points where our medium oscillates the most. So those are going to be our minimum and maximum amplitudes. Now let's look at this again, but let's do it from a free end. So now it's the same experiment, but now instead of a fixed end here, we're going to have a free end. It's pretty slow. Alright, so now we're hitting the end and we're reflecting, and it's coming back, the reflection is coming back the same way as the incident wave. So we're really seeing the same phenomenon. We've got nodes, we've got antinodes. The only difference is that now, since we have an open end over here, instead of there being a node at the end point, we have an antinode. Right? If it's open, it makes sense that this can vibrate, whereas if it's a fixed end, this can't move here and we would have a node. So from this video, we should have learned how incoming and reflected waves combine through superposition to give us something called a standing wave.